Okay, so we're very glad to have Professor Sreerup Raychaudhuri here. Professor Sreerup is a professor at TIFR in Mumbai. He did his PhD in Calcutta University with Alfred Raychaudhuri, and then he was a postdoc in TIFR and then at CERN. And then for many years he was a professor at IIT Kanpur. And in 2008 he moved to TIFR to help build the particle theory group there. Although today he's not going to talk so much about the science of what he does, the actual physics of what he does. He's going to give us a lecture on the history of science, and he's going to talk about the early days of particle physics in India. So many of us have been very curious and we've been looking forward to it. So over to you.
Thanks, Subrat. Thanks for inviting me. It's always a pleasure to be in ICTS. And so my talk today is going to be different from the usual talks you hear, because I'm going to talk about things which happened long ago. And so this is a subject which I got interested in a few years earlier. And when I was asked to write a review for the 100 years souvenir of my alma mater, that is University of Calcutta Physics Department. And then when I started reading up some things, then I realized that there was so much I didn't know and so many interesting things, little facets of information which I had no idea about and which I learned at that point. So I think it's nice to share that information. And there are lessons to be learned. There are question marks which arise because of this. But let me just start with the story. So I start my story around the turn of the 20th century, and by showing you this map and reminding you that India in those days was part of a worldwide entity called the British Empire. And therefore, the center of this was, of course, here. And if you had to communicate with England far away or with Britain far away, then you had to take this long sea voyage, okay, right round and go there. So some things happened at this end of this thin red line, and some things happened at this end of this thin red line. And remember, for everything, you had to take ship and go there and take ship and come back here. So there was a time lag. It was not the days of Google and internet, and you didn't get the information instantly. Things took time to come and so on. And therefore, developments also, there was a time delay in this. So let me start by reminding you that the story begins. So particle physics grew out of nuclear physics. And let me tell you, just by reminding you of the early discoveries here. So, of course, you know, 1896, Becquerel discovered radioactivity. And then in 1898, Gerard Schmidt and Marie Curie discovered that thorium is also radioactive. Then Pierre and Marie Curie discovered polonium radii, and Marie Curie coined the name radioactivity. That was in her thesis. Rutherford discovered alpha and beta rays, invented the concept of half-life. Paul Villard discovered gamma rays. Rutherford and Soddy by 1902 suggested that radioactivity involves the disintegration of atoms. This was Soddy used to look well. Then Rutherford and his student Thomas Roets did that famous experiment proving that alpha rays are doubly ionized helium atoms, again proving that atoms do disintegrate. Soddy and Fahans discovered the radioactive displacement law. And finally, by 1917, Soddy and his student Ada Hitchens from Aberdeen discovered the existence of isotopes. Now, why this silhouette? Because I looked the internet high and low. I couldn't find a picture of Ada Hitchens. I could only find a picture of her matriculation certificate, which has been put up by someone. So it's a pity that somebody who made such a fundamental discovery has sort of disappeared from the internet. And this is a theme which we'll see more of that as I go. Okay. Now, what about India? Surprisingly, radioactivity research started in India in St. Xavier's College, Bombay. And that was, so this is a picture of it as it used to be in the late 1890s. And there was a father, Adolphus Steichen. Again, I couldn't get a picture. So he was a graduate in physics from Göttingen, and he was a professor of physics there. And he had a colleague, another German father called Heinrich Scherp, and he was the professor of chemistry. And what did they do? That during this period, 1910 to 11, they journeyed to a place called Tuva, which is near Vadodara. Actually, it's very close to Godhra. And there are hot springs. And he went to study the radioactivity of the hot springs. Now, why was this interesting? It was interesting because there was a professor, R.R. Ramsay, from Indiana University, who had come up with this claim that hot springs the radioactivity increases with the flow of water and decreases when it falls, just sort of indicating to you that the heat is from radioactivity, which is partly true. But Father Steichen's paper, which was published, as you notice, much later in the Philosophical Magazine 1916, says that he and Father Shep found the exact opposite, that when the flow of water increases, the radioactivity seems to fall, and when the opposite happens. And they correctly interpreted it as saying that there are two kinds of things which are happening. The springs studied by Professor Ramsay were places where there was a radioactive material somewhere which was being washed away, and when the flow of water increased, it washed away more material. Whereas in Toa, the deposit was not in contact with the water, it was being leached by groundwater, so at a roughly constant rate, and when the flow of water increased, of course, it got diluted. So more of geological work, but this was radioactivity work in those days. Now, of course, soon after this, the First World War broke out in 1914, and then both Father Steichen and Father Shep, they were considered to be enemy aliens because they were German citizens. So they were actually put in an internment camp somewhere near Nainital, and it was from there that they had to get a lot of permissions to publish the paper. Later, Father Steichen in 1918, he was given he carried out a study of all the hot springs in the entire Madras presidency, which then involved all the southern states. And we have a memo that he was given the princely grant of 1,000 rupees to do this. Notice this figure because it was a 5-year project, and this 5-year project involved travel, stay, hiring assistants, everything for 1,000 rupees. Okay. And it's important in the context of some other figures I will mention as I come ahead. Okay. So now, where else did it start? In parallel, it started here in Bangalore. So this is a grainy picture of the old building, which is still standing, of course. So Herbert Watson, he was a young assistant professor at the ISC, and what he did was that he realized that some of the oldest rocks in the Earth's crust are at Kolar, which is not so far away. So this is Bangalore, here is Kolar, Robertson Pit, and here are the Kolar goldfields. So there were deep mines, gold mines there, and which had been set up not so very long ago. Around the 1890s, the British had started putting up mines there. And so you could go about 4 kilometers down and look at those rocks. So they wanted to see if the radioactivity increases as you go deeper into the Earth's crust. And he had an assistant called Gosto Bihari Pal. Again, I couldn't find a picture. All the pictures I found are of the famous footballer of the same name. But there was also W.F.S. Smith, who was in the Mysore Geological Department. So the three of them, I have just shown you silhouettes because I can't find their picture. So their result was that they didn't find any radioactivity. So the negative results was first published in the Proceedings of the Indian Academy of Sciences, which came out from ISC in those days, and then in the Philosophical Magazine, 1914. Later, Watson left, he didn't stay too long in ISC. He went away to the University of London and became professor of chemistry there, and he's credited with having invented neon lighting, but he didn't patent it, and somebody else did that. That's just an aside. And Gosto Bihari Pal went back to Bengal, and he was a teacher in a college. He wrote a textbook and so on. Okay, let's take the discoveries in nuclear physics ahead by a decade. So we all know that between 1908 to 1910, Geiger and Marsden, everyone may not have seen Marsden's picture, they made a careful set of observations, the famous Rutherford scattering. And Rutherford proved that this data can only be explained if you have a nucleus. So we all know this. And therefore, the first elementary particle, I guess, the electron and the neutron were the elementary particles of those days. Niels Bohr applied quantum theory to this, we know that. Moseley proved that the charge on the nucleus is equal to the atomic number, really best proof of the Bohr theory. Then in 1920, Rutherford predicted the neutron, but he wasn't sure. He said it's a possible hypothesis, and then he backtracked a little bit. Only in 1931, Ivanenko at Leningrad, he predicted the neutron based on quantum mechanics and using the famous argument about beta rays, that if you confine the beta rays inside the nucleus, they'll have too much energy and they can't stay there because of the uncertainty principle. And in 1932, the neutron was discovered. So at this point, you suddenly had particles. So the nuclear physics sort of is a transition between nuclear to particle physics. Now what happened in India? So I couldn't resist showing you this iconic picture. This is J.C. Bose with all his students, and they were all famous for some reason or the other. Meghnad Saha and S.N. Bose, everyone knows about. The other people were well-known mathematicians, general relativists, and so on. J.C. Ghosh was director of ISC after Raman, and so on. However, the person I want to concentrate on is this guy, Sir Devendra Mohan Bose, or D.M. Bose, who is well known as D.M. Bose, and he was J.C. Bose's nephew. So, in 1907, so remember in those days, there was no postgraduate science education in India. You could do an undergraduate degree and then you had to go to England or somewhere else to get a postgraduate and get a master's degree. So in 1907, D.M. Bose sailed to England and he enrolled in Christ's College, which was also the college of his master, and which had very famous people there. So he was two of the famous people who were his teachers, J.J. Thomson and C.T.R. Wilson. And in particular, he liked the work of Wilson, who had invented the cloud chamber. So this is really the actual cloud chamber built by Wilson. And this is an actual picture of some nuclear disintegration taken by him in 1911. So Bose worked with Wilson and learned how to build a cloud chamber. And he did all this interesting work there. He finished his PhD. And no, he didn't finish his PhD. He finished his master's. And he came back to India. In 1913, he returned to India and he joined the City College, which is nowadays called the North City College, and this is how it used to look in those days, and as a lecturer. But within a year, he was appointed the Sir Rashbihari Ghosh Professor of Physics at the new Department of Physics at the University of Calcutta. Now, I should say something about this because this was the first postgraduate department in India, and it was Sir Ashutosh Mukherjee who started out as a mathematician, then became a famous lawyer, and was the first Indian Vice Chancellor of a university in India. And it is he who decided that you should have postgraduate science in India. So he founded the science departments. And he is the guy who appointed Bose. Now the money for this, they came from Sir Rashbihari Ghosh, who was again a very well-known jurist and a lawyer, and he donated more than 21 lakhs to Calcutta University for this purpose. Remember, this is the same period, 1914, as 1,000 rupees was enough for a 5-year project. So you can imagine the generosity of this person. You can also imagine that I'm sure he didn't pauperize himself, so he must have had enough money. So that's the kind of money you made as a lawyer in those days. So just an interesting aside. So this Ghosh professorship came with a Ghosh traveling fellowship, for which the incumbent was supposed to travel abroad somewhere for 2 years and acquire some special skills and come. And Bose immediately decided that he wanted to go to the laboratory of Erich Wegener in Berlin. Now, who and what was Erich Wegener's work? So Erich Wegener was at the Berlin Agriculture University, but he wasn't doing agriculture. He was looking at cosmic ray fluxes. So this is Wegener with his instruments. And there is this famous quote from Bruno Rossi, who says that in the late 1920s and 30s, this technique of self-recording was brought to an unprecedented degree of perfection by the German physicist Wegener and his group. So we owe some of the most accurate measurements and so on. So he was doing very high quality work, and Bose decided that he wanted to learn that kind of work. So this also shows you that, remember, cosmic rays had only been discovered in 1912 by Victor Hess. And in 2 years, that means that he was very up to date, despite the fact that journals and everything had to come by ship. It took 3-4 months. And he was up to date. So he decision to go shows you how much I was up to date at the time. Now, what had happened to the German fathers and Xavier's, the opposite now happened to Bose. The First World War broke out there, and he was interned as an enemy alien, so in Germany. However, the Germans treated him better than the English treated the Germans. He was not interned. He was only required to report regularly to the police, and he was allowed to carry out his research work. So they didn't stop him from doing that. They didn't take him away. But he was only asked every week, you go and sign somewhere. Okay, so Bose made the best, and then but he was not allowed to come back to India when his fellowship expired. So they kept him on in Germany, and he utilized the time well. So in Berlin, he successfully built a cloud chamber, and he managed to record the recoil tracks of hydrogen particles, protons, produced by fast alpha particles. Now the reason why this is important is that at that time people didn't know where the momentum would be conserved at the atomic scale. So the fact that hydrogen atoms are recoiling is a proof that momentum is conserved. So this was, and of course that was later used brilliantly by Compton, as we know, to get the Compton effect. But here was one of the first proofs that moment. So these recoil tracks, this is from an actual picture in Bose's paper, and he did find. So it's very difficult to read these tracks, but I suppose those days people could. In 1919, he was awarded a PhD by the University of Berlin for this work, but part of this work had already appeared in 1916 in the Physikalische Zeitschrift. Bose also made the most of his enforced stay in Germany. So he was in Berlin, so he went to listen to Max Planck's lectures. And Max Planck used to give a series of lectures on physics, and Bose loved them. He says, after attending Planck's lectures, I learned what a system of physics meant, in which the whole subject was developed from a unitary standpoint and with a minimum of assumptions. But Bose was not the only guy who heard Planck's lectures, and other people had different opinions. For example, this is Pius didn't like. Okay. So then in 1919, after the World War was over, Bose was allowed to return to Kolkata. By the time the famous Rajabaja Science College building had been created, and he came back here to resume his position as Rajbehego's professor. But now he was no longer the only chair professor. There was another chair professor at the university, and that was C.V. Raman, who had become the Tarak professor of physics. And C.V. Raman was in the civil service, he was in the audit account service, and in 1917, he had been persuaded by Sir Ashutosh to abandon his government job and take up an academic position, and the pay was only 1,000 rupees a month, whereas earlier he was making 2,000 rupees a month. Now once again, compare the scales. So that's 1 month's salary was enough to drive a project for 5 years. Okay, we don't get that kind of salary nowadays, despite pay commissions. Okay, so, but this Calcutta University Physics department at that time was full of bright sparks. There was Meghnad Saha, there was S.N. Bose, there was S.K. Mitra, and there was B.B. Roy, who was a very well-known spectroscopist, who worked with Bohr and Hertzberg and so on. It was a really stellar department. There was P.C. Mahanabes at Presidency College, so. Now, Bose continued to do his alpha particle work. So, here is a publication in Nature, and he writes about his experiments in photographing tracks of alpha particles and so on. And he had a student called S.K. Ghosh, Subodh Kumar Ghosh. Again, I couldn't find a picture, it's disappeared from view, but it was published in 1920, I think. Okay. This was not the only place. There were other places where people were doing work. So at the Maharaja's College of Jaipur, in Jaipur, there was a gentleman called M.F. Soonawala, and he wrote a very interesting paper in the Indian Journal of Physics, suggesting that all nuclei are made up of electrons, protons, and the noble gas nuclei. So it was an early version of so he didn't know about this stable shells. So he thought those are elementary particles. So it's an early version of this Aufbau principle, trying to explain the periodic table. And so Soonawala had a lot of other students and so on, and who written praise of him. So he was, again, I couldn't find a picture of Soonawala anyway. There was A.C. Banerjee, who had become a wrangler at Cambridge. Wrangler basically means a graduate, somebody who had passed the immensely difficult Tripos exam. So he came and joined Allahabad University, and he was one of the first people who knew quantum mechanics well in India. So by then, M.N. Saha had moved there. So Saha and Banerjee, they wrote several papers applying quantum mechanics to the study of nuclear spectroscopy. So this was happening in Allahabad. And there was another gentleman called B.M. Sen, who was also became a wrangler from Cambridge, and he came to Rajshahi College, which is now in Bangladesh, and he wrote papers in Nature and the philosophy of beta rays. So in those days, relativity was a new thing, and he was applying them and to try to explain the spectral features, and also writing papers to try and prove that the neutron is a Dirac fermion. We take it for granted today, but at that time, those were things which people wanted to prove. So this is the only picture I could get from him. So B.M. Sen later became the principal of Presidency College. So there are some oil paintings of the old principals of Presidency College, and I asked a friend in Presidency College to get me this picture. All right. Now, this is where I think particle physics, nuclear physics moved into what I could definitely call a particle physics paper. And this was written in Allahabad by Meghnad Saha and his student D.S. Kothari, and who was an MSc. It was an MSc project. And let me try to explain this because it's a very cute idea. So if you remember, all of us have studied this, that in the 30s, the problem was to explain that why a neutron became to a proton and electron, why the electron had a continuous spectrum instead of a line spectrum. So here is a paper of measurement from 1935, this continuous spectrum. Where does it come from? And today, of course, we all know the answer. It was given by Pauli in 1930, and it was simply that there's a neutrino emitted which you don't detect, and it carries away an unknown amount of energy. But in the 1930s, people were not so comfortable with the idea of postulating new particles. So I thought this to be some eccentric idea of Pauli's, and the attempt was to explain it without doing this. So what Saha and Kothari suggested was the following. So they said that the beta decay process is actually a gamma ray emission from an excited nucleus. Let me show you a cartoon of this first. So imagine there's a nucleus and it emits a gamma ray. Now in the field of the nucleus, this gamma ray does a pair creation of an electron and a positron. One is absorbed by the nucleus and one goes out as the beta ray. And the one absorbed by the nucleus picks up an unknown amount of momentum. So this momentum is not quite all the momentum of the gamma ray, it's some unknown amount of momentum. So you can get a spectrum out of that. So it's excess momentum is taken up by the nucleus, and since you can't see that, you can explain the unknown things. Very nice idea, and this was published in Nature. It's not very often that an MSc project gets published in Nature. Okay, well, nowadays Nature is more difficult to publish in than it was then, but still, it was still the leading journal. So, of course, one of the reasons why this was taken very seriously is that beta decays are usually followed by gamma decays. And therefore, in the same radioactive sample, you would see both beta and gamma decays happening. And therefore, and the nice thing about this theory is that it doesn't require a neutrino. Now, unfortunately, in the same year, or a year later, came Fermi's theory of beta decay. And the Curry plot in 1936, done in great detail, it matches perfectly with the Fermi spectrum and not with the Saha spectrum. The Saha spectrum falls off like this, it doesn't give you this. So it didn't match with this. So this was the Curry verification which killed the Saha. So Saha fought for his theory for a couple of years, but then it was killed by this. But nevertheless, I think it was a very cute idea. Okay. D.S. Kothari, after that, he went off to Cambridge to work with Rutherford. All right. Now, interlude, I'll tell you the story of Max Born in India. And again, that's a story which has to do with Bangalore. So as you know that in 1933, Hitler came to power and the Jews started escaping from Nazi Germany to wherever they could. So C.V. Raman thought this is a good opportunity, let's try to get some very good physicists to India. So he had just become a director of ISC. So he tried to catch Schrodinger and Max Born. So Schrodinger wrote a few letters and then finally said he's not coming. But Max Born was interested. And in those days, Born was also interested in Hindu philosophy and other things. His wife was very deeply interested in this. So they decided that, okay, they'll come to Bangalore to see what happens. So in 1935-36 winter, Max Born and his wife Hedwiga, or Hedy as he used to call her, came to visit ISC Bangalore. And here you see a picture. This is Born, Raman, Mrs. Raman, Mrs. Born, and the rest of the faculty as they were. This is the building, of course. You're probably all familiar with this. So now Raman as director, he couldn't give Born a permanent job. He could give him only 1 year visiting professorship. So he gave him that position. And while he was doing this, there was a very bright student of Raman's whose name was Nagendranath. But I'll come to this first. So Professor and Frau, they liked Bangalore. Bangalore was not the Bangalore of today. It was a very beautiful, very quiet, very scenic city. And they wanted to settle here because Europe was a country where there was a lot of war frenzy. Okay, as a Jew, he was particularly affected. So this was far away from, it seemed very peaceful and nice, and seemed to be far away from all the politics of Europe. Now, Raman Aziz, as I wrote this, and in Nagendranath and Born, they wrote a very interesting paper called the neutrino theory of light. So this pursued an idea, of course we know it's wrong, that the photon is a composite of a neutrino-antineutrino pair. So the spin half minus half, and they combine and give you a spin 1. And this motivation, of course, was that the neutrino is massless, the photon is also massless, and of course this is wrong. But this idea survives the fact that the quark-anti-quark pair spin half minus half, and they combine to give you a spin 1 rho meson. So the idea survives. And this was the paper they wrote. Yes.
This is the progenitor of the notion of ozonization
Yes.
solution.
Absolutely. So this is, yes, that's a nice point. So indeed, this was the first paper, so written with this idea. It doesn't, I think this paper doesn't get the kind of importance it should. Okay, so then after this, Born, after doing all this, he decided he wanted to stay. So Raman put his name up for a permanent position at the ISC. Now this became a disaster. So what happened, in the ISC faculty, there were a lot of people who were opposed to Raman, so they decided that the best way to oppose Raman is to oppose his candidate, even if that's Max Born, because they didn't know about him. So an Englishman called William Aston, who was an electrical engineer, who didn't know about quantum mechanics, he stood up and said that the IIC should not create a chair for a second-rate foreigner who could not find a place in his own country. This was Max Born. Okay. And so the ISC faculty decided that they would not, that they would keep the thing hanging. Let Born stay for a longer period. This was ISC after all, it wasn't any other institute. So he had to prove that he was worthy of staying in ISC. So maybe after a year or two, they would reconsider his case.
What year was this?
1936. Much later, 54. 54. So if he had come with a Nobel Prize, it would have been a different story. But by then, all his students had Nobel Prizes. Okay. So, yes. But then electrical engineers didn't know about his work. However, the man who did know about his work, who was a member of the ISC review committee, so that review committee, so Raman appealed to the review committee, which was like the council, and they said ISC is for industrial research. Why are they trying to employ a mathematician? And among the people who signed that letter was Midas, who certainly should have known better. But of course, so let me come to my next statement. In his autobiography, Max Born writes, after the meeting, he was sitting there at the meeting. After the meeting, I went home to Haiti and cried. But I think it is the Indians who should have cried. So that's the story. However, so Max Born went away to Edinburgh, where, of course, the rest, so where he got nice students like Rudolf Piles and others, so, and Neville Mott, and so on. Anyway, however, it is true that all the disorders which were affecting Europe in the 1930s didn't affect India too much. We were busy with our own disorders, civil disobedience movement and so on, but it didn't affect the world of science. So Meghnad Saha at that time was working on his theory of monopoles. So he tried out a theory that this neutron is a bound state of two monopoles, so what we would call dyons today. And it would explain why the neutron is neutral, but it has a magnetic dipole moment. So it's an opposite charge, so it's a dipole in that sense. And of course the theory didn't last, but we know that Saha's derivation of the monopole is not so elegant, but this is half-page derivation of the existence of monopole directly from Maxwell's equations. So that is, of course, is in the textbooks. Now, of course, we know that the magnetic moment is because the neutron has electrically charged components. There was a gentleman called Kulesh Chandra Kaur and his collaborators who were in Kolkata, Presidency College, and they developed a theory of the atomic nucleus where the nucleus was the antithesis of the rest of the atom. It had a hard negative core and it was surrounded by alpha particles. It was a sort of mini atom. And this idea came from Rutherford, but what they did was they tried to apply quantum mechanics and use the Schrödinger equation and tried to build up the energy levels of the nucleus. So this is not so different from the nuclear shell model, which came later, but basically they took the orbit kind of orbital kind of interpretation too literally, so there were flaws in the work. Of course, today Kulesh Kaur has been forgotten for this work. He is better remembered because he opposed Einstein's relativity for the reasons best known to himself. And remember, a lot of people were opposing Einstein's relativity in those days, but that was mostly because it was the anti-Jewish lobby. So because Einstein was a Jew and they said this is metaphysics and so on, incorrect. But he had some scientific reasons, well, quote unquote scientific reasons. And then there are these websites today you find of alternative science, and he is very prominent in those. So. But anyway, I think there are better reasons to remember him. Okay, now, yes.
There was an English translation of the Saha and Bose.
Yeah.
What year was that?
1918. 1918. So I can tell you, since you asked the question, I can tell you a little bit, though it's not relevant to this. See, it was 1919. See, D.M. Bose, okay, so when Meghnad Saha and S.N. Bose, they joined Calcutta University as lecturers in 1914. the only senior person around was Raman. The other guys were all young guys. And Raman had a lot of books, but he was very selfish with these books. He would give them only to his own students, and he wouldn't give them to others. So, and his students were under strict instructions that don't give your books to others. So, in 1919, D.M. Bose came back with a lot of books. Okay, he had, but most of those books and papers were in German. So in order to do that, Bose and Saha actually learned German. They learned German and then they used it to translate. So this first translation came out after having learned German. And Bose later, when he went to work with Einstein, it helped him because he already knew German. But then he also, that's another story, he had to go and work with Madame Curie, for which he had to learn French again. So life was very difficult in those times. Okay, so now let me come to Homi Bhabha, of course. This is ICTS TIFR, I'm from TIFR, so one has to talk about Homi Bhabha. And in a sense, the work he did at that time was probably the one which is the most influential. So most of us all know that Homi Bhabha was a young Parsi boy from a wealthy family, and he was sent to Cambridge to study engineering. But in Cambridge, he heard lectures by Thomson, Wilson, Dirac, particularly Dirac, and determined to become a physicist. Now, he did that, so he was a protege of Dirac. And he spent a total of 9 years in Cambridge, during which he worked, among others. Fowler was his supervisor with Dirac, Pauli, Bohr, Fermi, and then, of course, Heitler. I'll talk about that in a moment. So now, Bhabha's 1936 paper, which was called Scattering of Positrons by Electrons, was the first calculation of Bhabha scattering. Now, what is the importance of it? And there are other processes, similar processes, Moeller scattering, pair creation also, which are typical QED processes. So why was Bhabha scattering so important? Why did Bhabha make such a name? I'll try to explain that this was one of the foundational works in QED. And remember, first of all, this was long before the days of Feynman diagrams. So everything had to be done from first principles, write down amplitudes and so on. But that's not the point. The point was, and I'll explain that now in modern language using Feynman diagrams. So I'll skip this part, that the real issue was whether the positron is an antiparticle or it just happens to be a particle with the same mass as the electron but a positive charge. How do we know that it's really an antiparticle? How do we know that quantum field theory is really true? Because in those days, a lot of people didn't accept it. They said all this idea is of particles, antiparticles, electrons, holes, all this they didn't believe in. So Bhabha set himself to calculate the cross-section for electron-positron scattering under two assumptions. One is that the positron is a different particle from the electron. It just happens to have the same mass, but it has an opposite charge. The other is that it is the antiparticle of the electron. So if you do that, there are two kinds of diagrams. There is what you call a scattering diagram, which would be true for any particle. I mean, you could put a proton here or any other particle. You exchange a photon and the electron. The positron remains a positron, and this scattering occurs. So if you do that, you get a cross section like this, which depends on cos to the fourth theta over psi. This is the famous Rutherford factor, of course. Now, if the positron is the antiparticle of the proton, there is another diagram. There is what you call an annihilation diagram. When these two can annihilate, and you get another diagram like this. And this diagram and its interference will give you two more terms like this. So the angular distribution now has another cos to the fourth theta, but it has a cos squared theta dependence also, and a sin squared theta here. So the angular dependence is different. So Bhabha's suggestion was, let's look at the angular distribution from experiments, and let's look at that and compare, and that will tell you whether which theory is correct. So the original results are not very clear, but I'll show you a picture. This is measured in 1970s, and here is the curve which corresponds to the annihilation diagram, to both diagrams. And here are the experimental data which match it so beautifully. And if you had gone with if you had gone with only this thing, you would get a graph somewhere like this. Okay, it's well below this. It would have been clear. But even the data of his time were good enough for him to say that, look, annihilation is actually occurring, and therefore quantum field theory is true. So this was the real importance of that work. Bhabha scattering is named after Bhabha scattering, not just because he did a calculation, but because it was the first to realize the implications of this calculation. All right. Then the other great thing he did was the Bhabha-Heitler theory. So Heitler was already a famous physicist. This Heitler-London theory had come out of the chemical bond and so on. He had a faculty position at 1933, but again he was dismissed for being a Jew, and he came to England and he got a position at the Wills Laboratory at Bristol. So Bhabha was at Cambridge, so they met over various occasions. And Bristol is not that far from Cambridge. So they were both interested in the same problem. How do high energy electrons in cosmic rays, how do they come through the 8 or 10 kilometers of the atmosphere and reach the sea level? Now, why is this a question? Because Bethe and Heitler had already calculated the energy loss by a high energy electron in the field of multiple nuclei of nitrogen oxygen, which is the air. And they had concluded that there was no way such electrons can penetrate more than about 2 kilometers. So that was the survival length. But here were these electrons which are coming through much more. And you would expect not to see too many electrons and positrons at the. So you've seen that. And you also see them on the ground. So what's going on? So a lot of people were convinced that the Bethe-Heitler calculation was wrong. But of course, they were careful people. So they had done it using QED. So people said, well, there's some problem with QED. So the idea was already the air that cosmic rays could produce cascades like an avalanche, that comes and creates more particles and so on. And Bhabha had heard this from Hugh Carmichael, I couldn't get a picture of him again, and from Heitler, from Lothar Neuheim at Munich. But these senior people, they didn't believe the Bethe-Heitler calculation because they didn't trust QED at all. However, Bhabha and Heitler set themselves to decide, okay, let's suppose QED is correct, let's suppose the Bethe-Heitler answer is correct, the Bethe-Heitler calculation. So they wrote this paper saying, okay, actually these are coming from cosmic ray showers. So this is a paper written from Cambridge and Bristol, 1936, communicated by Neville Mott. And this is the thing which gives the usual picture of cosmic ray showers, which you are familiar with. And of course, this also is Bhabha's lasting contribution to cosmic ray physics. Now, this paper was published in 1936 in the Proceedings of the Royal Society. 1 year later, see, information didn't percolate so fast in those days. 1 year later, in 1937, Carlson, Oppenheimer, and his student Carlson published the same results in the Physical Review, but they were too late. This is still called the Bhabha-Heitler theory. It's not called the Oppenheimer-Carlson theory. Okay, so those few years at Cambridge from 1935 to, let us say, 39, so these were years in which I call the Midas years because whatever Bhabha touched became a wonderful result. So like everything turned to gold. So in the first 1936, he suggested that there was something called a hard component of cosmic rays, which came directly to the ground, and he suggested it might be due to a new particle, but it's about 100 times more massive than the electron. And in 1937, Anderson and Demeyer had precisely discovered the muon. So in a sense, Bhabha had predicted the muon from that data. So that was a very insightful piece of work. In 1935, Yuka had predicted the pion as a spin zero particle. And then Bhabha had pointed out if the pion couples to a nucleon-antinucleon pair, then you can put the half plus half to get a 0, but you can also put half plus half to get a 1. So there should be a spin 1 particle as well. And that spin 1 particle was the rho meson, which was discovered only in 1961. So far before his time, he had made this prediction. So there would be vector messages also. The other piece of work is that he proved that the long lifetime of cosmic ray muons are due to time dilation. Now, this is an exercise which every MSc student does as a standard exercise. But it was Bhabha who proved it, and remember these were days when relativity was being attacked from all sides. It is Bhabha pointed, look, here is an experimental proof of relativity right in front of your eyes. This is happening because of relativity. So in a sense, it was also courageous to participate. So this period at Cambridge was really fruitful and very wonderful, and Bhabha was certainly considered among the top scientists of the time. And that's why you see this nice picture of Bhabha with very, very great physicists. And from the picture, it looks like Bhabha is doing all the talking and other people are listening. Yeah, I know. So now, good things don't last. So, like mankind was banished from Eden, Bhabha had to leave his Eden. And the snake, of course, in this case, was Mr. Adolf Hitler. And in the summer of 1939, he came home from Cambridge to spend a vacation with his family. But then the Second World War broke out, and then civilians were banned on ships because there was an U-boat being submarine, so the danger of being sunk by a submarine, so all civilian things stopped. So Bhabha had to return, sit in India, and it would be 6 years before he could visit Cambridge. So now that he was forced to seek a job in India, So Bhabha did that between, so Allahabad University, which had, I think Kothari was there in Allahabad University then. And he was not in Allahabad University, but he was sort of acting for Allahabad University. And Raman at Bangalore, they were trying to persuade him to come to. And eventually he joined IISc, and Raman had promised him all help to build a cosmic ray group and whatever he wanted. But when he actually came, this is a story which experimentalists know very well. He gave him 2 rooms and said, now build a cosmic ray group. Okay. So Bhabha worked very hard on that. For the first time in his life, he faced the reality of doing science in a colonized country. He had to take the silver spoon out of his mouth and put an ordinary spoon and see how life was. And for 6 years, he worked very hard in Bangalore. He tried to set up an experimental cosmic ray unit, while at the same time he was pursuing some of his theoretical ideas. But I think it's fair to say that none of this theoretical work has the impact of his Cambridge work. It was nice, elegant, intelligent work, but did not have that impact for whatever reason. So I'm showing you 2 pictures. Bhabha trying to launch a balloon, and this is
Bangalore University.
Yes, Bangalore University, and the Bhabha-Corbin equations, nice paper on spinning particles, general spin, but again, not of so much use today. Then, having realized these difficulties, he became an institution builder. 1945, he founded the TIFR. This building, of course, is only 1962, but he became the founder of the institution. And then the Atomic Energy Commission started in 1954. You see Bhabha with an early prototype of the reactor and so on. So he got into other things. All right. Now let me switch tracks and go to the other end of the country and talk about experiments done at Sandakphu. So it starts with the discovery in 1910 by a Japanese scientist who was working in Cambridge called Kinoshita. And this is of course not the Kinoshita, it's well known now. But so he pointed out that charged particles will leave tracks in photographic emulsion, silver bromide, silver iodide, it precipitates the silver. So you get tracks like this. Now Kinoshita and his collaborators were interested in nuclear disintegrations, but the first people to point out that you could use them as cosmic ray detectors, this was pioneered by 2 ladies, Marietta Blau at the Radium Institute of Vienna and her student Hertha Wambacher. Okay. So they are the people who started this work and said that you could study cosmic rays by using photographic plates. And this work, I think, was a Nobel-worthy quality, but it's sad that both these women were victims of severe gender and political discrimination all their lives. I'll come to that in a moment, at a later part. However, how it affected India was in the following way. The 25th session of the Indian Science Congress was held at Kolkata in 1938. So in those days, it was not a mela as it is now, but it was a lot of serious science done there. And it was attended by various luminaries. It was supposed to be addressed by Rutherford, who passed away just before that. So Emensa actually read out his address. He had even prepared his address. So Rutherford gave the talk. And in the cosmic ray session, so Walter Bothe, who later won the Nobel Prize for the coincidence technique, and Jeffrey Ingram Taylor, who was the leading cosmic ray expert in Cambridge. So there was a lively discussion which they had led, and Bothe in particular, he was familiar with this photographic emulsion technique of Blau and Wambacher, and he talked about this. He said, here is a new technique which people can take ahead. So this discussion fell on fertile ground. And what was that? So D.M. Bose, who had just become director of Bose Institute, and he decided to try out this technique with the help of his student Bhabha Chowdhry. So what they did, so the idea was simple: take photographic plates, take them and expose them at high altitudes where other interference from atmospheric cosmic ray showers from terrestrial sources, radioactivity and so on will not come. So they didn't have a balloon facility. So what they did was they trekked to Tiger Hill and Sandakphu, which are near Darjeeling, to expose photographic plates to cosmic. Now this itself was a bit of an achievement. I'm showing you a Google map. This is Darjeeling here. So you needed to trek all the way. Now there are roads, but there were no roads. So you had to go on muleback or something up to Tiger Hill here and up to Sandakphu up there. So every week they would go up the hill and expose a set of plates and take another set of plates back. And from Kolkata. So they were going to Darjeeling doing this. So I mean, just the physical amount of work was a lot. But they carried it out for 2-3 years. And See, when they said exposed plates, those were not sheets of celluloid as you know today, but they were actual glass plates. So this was Ilford was the famous company, and they created what they were called this guy. So you got a packet of these plates, and this is how they looked. So you have a box full of plates, and then there were glass plates like this. So they were coated on one side with silver bromide or silver iodide or something, and you expose them, and so to expose them, you would need a camera like this. So older people in this audience have seen this kind of box camera. I don't think younger people have seen them outside movies. So you opened the front of this, you opened something here, and you push the plate into the back. And there was a little rod with which you pushed it in, and then you shut the camera, covered it with a cloth, and then exploded it. So that was how all these famous pictures of the Second World War were taken. But anyway, what our friends did was that they wrote this paper, the photographic plates as detectors. Here is their paper. Photographic plates as detectors of mesotron shots. So mesotron was the early name for, Yukawa's name for the meson. So they have been using photographic plates and new half-tone, I'll come to this half-tone in a moment, for the study of cosmic rays and so on. And this is signed Bose and Chowdhry. And notice the citations, Blau and Wambach are both there, other famous names also there. But that's the... Now there is a question, did they discover the Pion? So I'm going to take up this question because it's been rumored in many places and also stated in many places that they had discovered the Pion. So what had they actually discovered? So first of all, I should mention that during this, so there were two kinds of plates. There were half-tone plates which had the silver bromide coating on one side. There were full-tone plates which had the coating on both sides. So the full-tone plates had better resolution. They captured the photons better. Now, during the Second World War, only half-tone plates could be bought. All the full-tone plates were reserved for this war reconnaissance work. Planes would take pictures of enemy territory, so they were all reserved for that. So even an English civilian could not have bought a full-tone plate, and let alone people who are not English. So they had to work with half-tone plates. Now, here is a picture with a half-tone plate. So you see how grainy and indistinct it is. The resolution is low. And what is this building? Howrah Station, yes. And this is a modern photograph. So you see, the building hasn't changed, but the quality of the photograph has changed vastly. This is 1918. So here is the table from what they had measured, and they give everything in terms of the electron mass. So remember, this is the muon mass as we know it today. This is the pion mass, charged pion as we know it today. And see, these are the masses of what they measured from the tracks. And if you look at them, there is only one mass here. This is their average mass, far below any of them. Of course, the resolution was low. Errors are large. You see, the error is huge. But there's only one mass here, which is anywhere near the pion mass. The rest are more like muon masses. So it's likely that what they had seen were mostly pions. Okay, and this is as likely to be a fluctuation. So, well, yeah, what they had seen were mostly muons. And it's unlikely they had seen the pion. Certainly, the fact that the pion decays to muons, this was not possible with the kind of data they had. So the claim that they had discovered the pion is probably not a fair claim. But certainly they had pioneered looking for mesons. There's no question about that. Okay, the actual discovery of the pion was done by these four people. Powell is the boss of the lab, Occhialini, Merhet, and Cesalates. And after the Second World War, Patrick Blackett had done a lot of war work, radar and other things so the British government was willing to listen to Blackett at that time. After the war, scientists were suddenly popular because they had helped to end the war. So the government asked plate manufacturers, make densities, high density plates, ostensibly for the Cold War effect. But Blackett was clever. He said he also gave the things which are useful for scientific work. And Lattes had suggested that if you put a little more boron in the emulsion, the sensitivity increases. And in fact, it increased like magic. And we have this very poetic words of Powell. It was as if suddenly we had broken into a walled orchard where protected trees had flourished and all kinds of exotic. So suddenly you started seeing new things. And among the new things they saw were these tracks. And you see here, so this These are actually pion discovery tracks. So what happens is the following. So you have this track here, which you identify as a pion. A pion came this way, decayed to a muon. This long track is a muon, and this one which I have drawn is an invisible neutrino. The muon comes all this way and then decays here to a electron, and then there are invisible neutrinos. So this happens with all of them. So the fact that now you have this kink here, this shows you that a decay has occurred, and this little track is clearly a different particle from this, and this was the charged pion. So this was the discovery of the pion. Now, this 1947 work, it clearly showed the existence of these two mesons, and the fact that you are producing lots of pions shows you that it interacts strongly, and therefore this is the Yukawa particle. It has strong interactions. Now, once again, this was not the first. It had been suggested by these Japanese, yes, it had been suggested by the Japanese people in 1942 and 1943, but because of the war, the Japanese journals were not going out of Japan. So nobody had seen them. And so that Bethe and Marshall made the same proposal in 1947 at the famous Shelter Island Conference, but they did not know at that time that Powell and so on had already published this. But after that, it became well known. So when it came to distributing honors, so Cecil Powell walked away with a very well-deserved Nobel Prize in 1950. Occhialini returned to Italy. Later, he was awarded the Wolf Prize for this work. Cesar Lattes, who had given the idea of putting more boron, he returned to Brazil and he became a leader of cosmic ray research there. Hugh Muirhead actually did some very fundamental work on parity violation in the 50s, and he wrote a famous textbook which at one stage was the standard textbook for us. Now what happened to Marietta Blau? She never got a regularly paid position. She was dismissed from the Radium Institute by the Nazis because she was Jewish, and then she couldn't get any position. She got a temporary position in Mexico and eventually had to do it all. And eventually she contracted cancer from her early exposure to radiation, and she died in 1972, in 70. Hertha Wambacher, who had an even sadder life, during the war she turned Nazi, tried to take over Marietta Blau's lab and so on. After the war, the Russians imprisoned her and took her away to Russia. And then when it became clear that again she had cancer, they released her, but she came back to Austria and died in 1950 at the age of 37. So this is the sad part of the story. But in this part of the story, one has to add that there is no mention anywhere in this, all of this, of the work of Bose and Chowdhry, who had been pioneers in this work. So the only thing I can say about this is to quote from Tennyson. So he said, it is better to have loved and lost than never to have loved at all. So similarly, it is better to have tried and lost than never to have tried at all. And even more obscure than this, there was work being done at that time in Wilson College, Bombay, which is not even a very good college today. But there were two gentlemen there called Dabholkar and Taylor. And look, behold, in 1936, before the Science Congress, they were already using alpha particles in photographic emulsions. So Taylor was a student, had been a student of Rutherford. Dabholkar was his colleague in Wilson College. And you look at this paper, numerous alpha particles on Ilford art plates, all the same things they had done. Later, they even exposed things at Mahabaleshwar and so on. But of course, in Wilson College, then resources were limited, and the work never went very far, nothing. But they, of course, didn't look for mesons. But you see that they were doing frontline work from an undergraduate college, which is impressive in itself.
Which journal is this possible?
Sorry?
Which journal is this?
Nature.
Wow.
Maybe this is not Nature. This is probably the Proceedings of the Royal Society. But that was sort of equivalent to Nature in those days. The print is not Nature, so I think it must be Royal Society. Okay, so now let's talk about somebody else. So let's talk about Vikram Sarabhai. And so that tells you. So Vikram Sarabhai could have chosen a different career. So. Like Bhabha, he came from a rich family. He went to Cambridge and did his typos. More courageous than Bhabha, he risked his life on the sea voyage in 1940 and came back to India. And Raman, who had this jeweler's eye for a brilliant guy, he immediately snapped him up and said, I'll give you an assistantship, come to ISC. So Sarabhai went to ISC, but remember he was a young fellow. In 1940 he was only 21, and then there was already Bhabha there. It was a big name and fame. But he decided, he was interested in cosmic rays, but he decided not to attach himself to Homi Bhabha. Okay, it would have been the natural thing to do. Okay, he was 10 years older, was already a famous name and was already doing a lot of cosmic ray, but he decided to do his own stuff. And he had the courage and confidence at the age of 21 to be able to do this. So during his stay, again 6 years of the war, so he wrote a series of single author papers from there. For example, here is one from 1944, here is another one, 1945. So his interest was more on the effect of the Earth's magnetic field on the cosmic rays. Not so much on the constituents of the cosmic rays themselves, but more on the effect of the Earth's magnetic field. And then in 1946, he went back to Cambridge, and there he submitted a thesis called Cosmic Ray Investigations in Tropical Latitudes. He got his PhD based on this work. Like Bhabha, in 1947, he came back to India, and he collected money from his own very rich family and from other rich industrial friends to found the PRL. He was 28 years old. But he was wise enough not to take up the directorship immediately. So he roped in Raman's former student, K.R. Ramanathan, you see him here, who had retired from the Indian Meteorological Department, and he roped him in as the first director. So only when this Ramanathan retired in 1965, which was many years afterwards, then Sarabhai took over as director. Before that, he remained a simple professor in PRL. He trained 19 PhD students, and that include the last of them was the late U.R. Rao, who used to look like that in those days. And those who have seen him around, I mean, he died last year. So will like this picture. And Sarabhai was a very simple person, and he worked immensely hard. In fact, he worked so hard that people say that he worked himself to death. He died at the early age of 52. Now, one of the things about Sarabhai, his interest started from cosmic rays to the Earth's effect on cosmic rays to planetary magnetic fields, from planetary magnetic fields to solar physics, because that's their origin, from solar physics to satellite-based observations, and eventually decided that we need to launch our own satellites and rockets. So therefore, he moved towards that direction. So today, we have, say, became the father of India's space program. That's how his interest went. And you see a picture of him with another important person in India's space program. So, can anyone recognize the other person? This is Sarabhai, of course.
Person looks like Kafir Ahmed, but
No, no, no. This is Abdul Kalam, without the hair. And of course, so today when you see these nice pictures, you know this happened because this guy looked at the sky. Okay, now let's look at the cosmic ray group at TIFR in the 1950s.
Did he spend some time also at ISC?
Yeah,
But after that he went to here he never came.
no, he didn't come to ISC, but he didn't come and work here.
Oh, I see. So at a very young age he moved to Ahmedabad and never came.
Ahmedabad was his hometown anyway. Okay, so in the 1950s, so Homi Bhabha of course had founded the group, but he was then mostly involved in setting up the BRC and the DA. So he was not so much in the science. I mean, he would come on Wednesdays and listen to what people said and went away, give his opinions. The main person who was running the show was Bernard Peters. So Bernard Peters, his actual name was Bernhard Petrovsky, and he had an interesting life. His parents, he came from Poland. So his parents escaped from Poland to Germany to escape the Russians. Then he had to escape from Germany to the US because he was Jewish and in the Nazi period. Then he had to escape from the US because he was a communist, and he came and escaped to Bombay. Then at some stage, he escaped Bombay and went to Copenhagen, where he became the director of the Niels Bohr Institute. And some people say that he was escaping from Bhabha, but I don't know whether that's true or not. So he was the leader of the show at that time, and he was already a famous guy. He had worked on the Manhattan Project and so on. Then there was M.G.K. Menon. Oh, okay. So now I have to put another date on this, but sadly. But he was a student of Powell, and he joined TIFR in 1955, and of course we know that he succeeded Bhabha as the director. So Menon was the young Turk, and Bernard Peters was the most senior guy, so they were driving the research, lots of students, few. Then there was Devendra Lal. Okay, there was Srikantan who was a student of Bhabha. So Srikantan is the only person among this group who is still with us. And he was Bhabha's PhD student. And I'll tell you about his work. There was Devendra Lal, Peter's student, who later moved into Earth Science and Oceanography, also went to PRL, I think, as his director. Finally, there was Yashpal, who came and worked for a little while in TIFR. Then Bhabha sent him to MIT to do his PhD with Rossi. He came back to India, then he again moved to various places. He was a very famous chairman of the UGC. This is how he used to look then. And this is the face which is the more familiar face of Turning Point, which most people remember him by today. Okay, so this was the group. And of course, there's a long list of PhDs done in those days. So you see, first were all Bhabha students, then you see other people coming in. And here is Srikantan, Bhabha student, then Devendra Lal, Peter the student, and so on. R. Vijayaraghavan, Bhapinder Bhatti, and so on. Okay. Now, the 50s, according to me, were a fabulous period for particle physics. There are many discoveries. Okay, all these long series of particles. Young's theory came in 1954. Intermediate vector bosons due to, and 1957 due to Schwinger. V-A theory, Shuddha Sudarshan, Late Sudarshan, and Marshak. Priority violation came in 56. Even the renormalization group, the first papers had been written by Stuckelberg in 1953. So it was a grand period for physics. But where was India? The TIFR group in India, particularly Indian cosmic ray research in general, was nowhere involved in all these developments in particle physics. Now, part of this was because of Bernard Peters, because he had diverted much of the work to the production of exotic nuclei. So exotic isotopes, exotic in cosmic ray collisions. In some sense, this is a research dead end because you could do much better at reactors later. So, I mean, soon after this came reactors with enough luminosity, with enough flux to give you these things anyway. And then TIFR didn't have another theorist of Bhabha's caliber. As we know, Sudarshan came and left, S.N. Biswas came and left. And Bhabha himself was too busy. Bose and Saha were already past 60, were aging. And B.S. Kothari, of course, who was still, but he was then advisor to the Defense Ministry, so spending most of his time in South Block. So there was nobody to take up the cudgel. And so at that time, I think there was the entire Indian cosmic group missed the bus by not being part of the real mainstream, or the developments which took us further. Okay. The one thing which was really in the mainstream was the Kolar Experiment. So younger people here don't know much about the Kolar Experiment. So let me tell you about that. So this is a blow up of that same picture. We are here. Where are we? Here. Somewhere here. Anyway, so you see Kolar is not far away. And then from Kolar, you need to go to this town called Robertson Pet, and the Kolar goldfields are next door to that. So they are not far from here. So at Kolar, there are these gold mines. So this was the favorite mine. This was the mine which allowed people to do science there. The Champion Reef mine set up in AD 1900, as you see. So here, so the Champion Reef mine, there are these things which go down up to 3.2 kilometers, and then there are shafts which go down actually all the way up to 7.3 kilometers. So all these places used to have gold-bearing rocks. So now it's of course, it's not worth bringing them out anymore today. So as early as 1948, Bhabha sent Srikantan and to Kolar, and he was assisted by these two people who were then scientific officers, Naranan and Ramamurthy, and said, go and measure the cosmic flux at depths of 10,000 feet or more. And what happens is that as you go, the Earth shields the cosmic rays, so the cosmic ray flux keeps dropping. Okay, so whatever this is. Of course, Kolar is somewhere, would be somewhere here on this thing, but it's not doesn't feature on this because mines are closed. Now, what they found was that initially the flux was declining exactly as expected, but then unexpectedly it began to rise. So they wondered what's going on, and it was Bhabha who correctly guessed that there must be some radioactive rocks down there, and in fact there are some thorium-250 in Kolar at depth just above 2 kilometers. But when you go further, then again this vanishes and it goes back to this curve. So that was the result. Now, by the time you go down to about 5 or 6 kilometers, then the cosmic ray flux disappears totally. Now it was shown, now this is interesting, so no, not that much, 2.7 kilometers. Cosmic rays had gone. So if the surrounding rocks are inert, nothing would be detected. But in 1955, the neutrino had been detected, And in 1957, this Russian gentleman called Markov realized that, of course, neutrinos can penetrate. They can penetrate the whole Earth. So if neutrinos go there, and then they do an inverse Compton reaction with the rocks, or the nuclei of the rocks in the Earth, then you would suddenly see muons. And those muons can come only from neutrinos. So if you see those muons, then you are seeing atmospheric neutrinos. So in 1957, the TIFR group immediately took up this suggestion, and there was this student who was young then. He's not young in this picture, called V.S. Narasimhan, who took up a major role in setting up the detector and trying to look for these muons. And it was a very successful thing. So here we see that in 1965, we have this paper. So it's a collaboration, detection of muons produced by cosmic ray neutrinos deep underground, very clear. So we see Narasimhan, M.G.K. Menon, Ramanamurthy, and Srikantan, and collaborators from Osaka and from Durham. And this paper is received 12th July 1965. And they were able to beat Frederick Rayner's discovery of the neutrino by 14 days. So this paper, they had done the similar experiment in a gold mine deep in South Africa. So it says some. So that's why. So they were doing this from Ohio, but here you had to. They were in South Africa for this. So here is one discovery which was made before anyone else. In the 1970s, the Kolar experiment was revamped to look for proton decay. And of course, no events were found. Even today, no events have been found. However, from 1975 onwards, some weakly interacting particles of mass around a few GeV seem to have passed through the Kolar detectors. So there's speculation that could these have been the first. We have not detected dark matter, but maybe one day we will say that that was the first evidence of dark matter. This suggestion comes from G. Rajashekharan in Chennai. And I gave this talk at Chennai, and he scolded me for not putting his name on this. So I'm being very careful to mention the name. Okay. So the Kolar experiment was closed down in 1992. And the Kolar mines themselves were shut down in 2001. So if you go to Kolar today, it's a picture of abandonment and desolation. So this is the same champion reef mine. So, all right, so I can take a few more minutes. So let me look at particle physics and go to North India. And there was this nice group of M.N. Saha in the 1930s, which flourished at Allahabad. But when Saha moved to Kolkata as director of the Association for Cultivation of Science, his students moved with him, and this group collapsed. Except for A.C. Banerjee, there was nobody else. Then, in 1939, D.S. Kothari returned from the UK and to found the physics department at Delhi University. And R.C. Majumdar, who was Saha's student, moved, and together they built the physics department at Delhi University. I'll come to this in more detail. Separately, P.S. Gill built a cosmic ray group at Aligarh Muslim University. So let me tell you a little about P.S. Gill because he's a very interesting character. So he was born in a farming family in Punjab, and he used to walk 5 kilometers to school every day, so from a really remote place. But after passing school, he got a job as a hand on a ship and worked his way somewhere to the US. Then he started as a taxi driver in Panama City. Again, made some money there and managed to get to the University of Southern California, and he did his BS there. He must have done well enough because the next we heard of him, he was in Chicago doing his PhD with Arthur Compton and cosmic rays. So Arthur Compton was the guy who was looking for this latitude effect, and this was what Gill's PhD thesis was on, which proved that cosmic ray primaries come from the solar wind. He also was one of the early people to show that the Pion has, experimentally, that the Pion has spin 0. So he's a very good experimentalist. He got his PhD in 1940. Now with these credentials, Gill could have found a job in the US, but he preferred to come back to India. So he came back to the Punjab, and there was the Foreman Christian College in Lahore, which is still there, and started cosmic ray studies at high altitudes. So first he would travel to Kashmir, to Gulmarg, like the Sandakphu people, and then when the Second World War was almost over, a lot of British warplanes were hanging around doing nothing, so he persuaded the pilots to take his plates up and do something useful for it. In 1946, he went on a lecture tour of the US and Europe, where he met Homi Bhabha. And Homi Bhabha persuaded him to come to TIFR in 1947. However, Gill and Bhabha didn't get along, so within a year, Gill was back to the US. And from there, again he was lured back to join Aligarh Muslim University by Dr. Zakir Hussain, later President of India. And then Gill built up his own cosmic ray group at Aligarh, where the main focus again was not on the elementary particles, but on nuclear reactions, geomagnetism, shower profiling, that kind of stuff. So that has always remained the forte of the Aligarh group since then. In 1963, Gill left, this is the Aligarh department, to found the Central CSIO at Chandigarh, from which this is the CSIO building today, and he retired in 1971, and still full of energy, he set up a business manufacturing magnetic heads for tape recorders. So somewhere in the outskirts of Delhi, he set up this. And eventually, when he was too old for that, he sold his business and went to live with his daughter in the USA, where he has written his memoirs. And the interesting about that memoirs, he has blasted every single scientist who was in India at that time. So memoirs make interesting reading, but not probably worth reading. All right, now let me come to Delhi. So the Delhi University had been founded much later by this gentleman, Maurice Dwyer, Sir Maurice Dwyer. And here we see him at the convocation at Oxford, where the convocation lecture had been given by Tagore. And of course, the other person here is Radhakrishnan. So this department, and still, this is how it still looks, these were the two people who founded it. So Kothari and Majumdar founded a complementary pair. So Kothari did a lot of government work, and therefore he was able to bring funds and a lot of help and people into the department. And Majumdar actually ran the physics department, and he sat with the students and so on, even with Kothari students. So but they worked very well together.
It's not been painted since then, I think.
No, that's not true. I just went through it, it's now painted.
But certainly at the time the photograph was taken, you can see the remnants of posters there. So.
Of course, it's been painted.
Okay, so, all right. But as early as 1942, Majumdar had this young MSc student called Suraj Gupta, with whom he published a paper on electron-meson interaction. This was not Gupta's most famous work, but Suraj Gupta went on to discover what is known as the Gupta-Blaloy. This is a page from Ijixin in Zubair. So from the Gupta-Blaloy indefinite metric. So they were training very, very good students. And Gupta is still alive somewhere in the US. And the other student with whom they wrote papers, of course, was Jogesh Pati. He also from Delhi University, wrote very nice papers. There are many other good people from Delhi University. And of course, Pati later went on to predict proton decay, which probably doesn't happen, but still was a momentous result in particle physics. Other good people in Delhi University. So it's interesting that Samrendranath Biswas, who was later known as S.N. Biswas, he was the co-discoverer of the lambda barrier. He was doing cosmic ray work in Australia. And from there he came to TIFR, but after a year, maybe he didn't get along with Bhabha also, he left and went to Delhi University. So, but in Delhi University he was a theorist. So he worked on current algebras, S matrix theories and so on. And he was affectionately known as Dada Biswas. And many generations of people grew up under his influence. A. Mitra, still alive, he did his PhD with Majumdar and then moved to, again, a second PhD with Hans Bethe, and he joined DU in 1963. He still comes sometimes. He's always worked on dispersion relations, bound states, Bethe-ansatz, that kind of stuff. So, as an aside, they couldn't get along with each other either. So, famously. All right. Finally, last thing I moved was group is.
You mentioned Raji Rajaram.
So, and there are many omissions. This is a long story. Yes. So let me finally come to Alladi Ramakrishnan, and you see a picture of Alladi Ramakrishnan with, I don't have to tell you, this is his son Sitaram Alladi, who is now a very well-known mathematician somewhere in the US.
No, son is Krishna's son. Sitaram is his nephew.
Oh, Sitaram is his nephew. Sorry, son is Krishna. Thanks. Well, you are the person who knows this best. Okay. All right. So Alladi joined TIFR in 1947, and surprisingly, so Bhabha asked him to use stochastic methods and study cosmic ray showers. And one thing which is true is that this is the first example of applying Monte Carlo methods to particle physics. These are the bread and butter of particle physics simulations today, but nobody remembers that this was started by Bhabha and Alladi. But this was the first people to develop a cosmic ray shower using probability ideas, but nobody acknowledges this work. But that is what he has done. Then he went off to the US to do his PhD, And when he returned to India, he joined the University of Madras. And then he didn't, he started this set of discussion group, seminar group, and the head of department didn't like it. So he told him that you have to stop this seminar group. So Aladi moved the group to his house. And they would meet every week and have this theoretical physics seminar. In 1960, Niels Bohr came to India. He went all around India. And then when Bohr had gone to Delhi, so the journalist, especially from the Hindu, asked him, what are the things in India which impressed you? So he said, Bhabha has built this grand institute, very nice institute in Bombay called TIFR. And I also like this little intense discussion group of Alladi in Chennai, two ends of the spectrum, but he liked both of them. This is what he said. And this appeared in the Hindu. And in those days, prime ministers used to read newspapers. So Nehru read the newspaper and he was impressed. So when he next came to Chennai, he asked the governor to set up a meeting with this guy. So Aladi came and then he asked him, how can I help you? So let's just give me an institute. So he gave me an institute and that's how my science started. Now, the people have other somewhat different versions of this story. This is the story, this is one version of the story. Anyways, it's the nicer version of the story. So, all right. So now, let me just show you this little picture, little movie. So particle physics, like everything, has been growing, grows like a tree. So it starts as a small sapling, you put out more and more leaves, you keep growing. And that is how it has grown in the West. That is how it has been growing in India too. But it takes years. It takes years and years for a subject to grow or for a discipline to grow, for enough places to be involved here. And it's, now in the West, it has grown, science has grown like that. It's grown into a mighty tree with many branches and so on. And in India, we are still somewhat behind. We planted the tree much later. The tree has been growing. It has set out roots. But it's not a mighty giant of the forest. We know that today. But we are growing. So it does take time. And let's see, this will be over in a moment. So, okay, let me just stop this and take it ahead. And let's see how things did grow in India. So by the 1970s, there were only these few people in places in India where you had groups doing high energy physics, cosmic ray research, that kind of stuff. In the 70s, came a few people. Pradhan founded the IOP. People started working at the University of Hyderabad. Mukunda came back to Bangalore and started the CHEP. Is that right? So, well, CTS in those days. A few people returned to IIT Kanpur and to BHU, so the number of places increased. The first DAE HEP symposium was held at IIT Bombay in 1972. And so when the 80s started, then there were more places. And during the 80s, the first SERC theoretical school was held at ISC in 85 in this city. The first string theory school was held at IIT Kanpur in 86. So Spent Avinash will have been there, I guess. And the first workshop on high energy physics, Web 1, was held at TIFR in 89. So I was there. I don't know if anyone else was there. Then in the 1990s, there came two new places which are now centers of high energy physics, HRI and IIT Guwahati. First experiment research school was held at TIFR in 1995. Now it's held annually or biannually. During the period 2000 to 2018, since the turn of the century, there have been many new places. So, where now there are groups of people who are doing energy physics, and we are supposed to have a new experiment, which started. Hopefully, it will start. It's but certainly there are the cards. So, here is the picture in 2018. These are all the leaves which have been put out. And from the way new institutes are coming up, I expect that in 2038, this would be the picture. So we are growing India in that sense, and the growth of fundamental physics, fundamental energy physics has grown from the roots which I showed you. Okay, so I should wind up now. I'll make some observations. Now, yes.
You did not mention about the TIFR's collaboration with CERN that
I didn't do that because so I've stopped my story in about 9. This part is just the growth of places. But there are many things happened after that, which I have not done. So I've stopped my story at around the early 60s. So yes, these things happened from the 70s onwards. Yes, so I want to make some observations about this early growth, and I'm starting by folded hands. I don't want to hurt anyone or to criticize anyone. These are just observations which struck me while going through this history. The first was the tremendous influence you see of Cambridge University and the Cavendish Laboratory. This is the old Cavendish Laboratory used to be. So you see that the impact of people's work, so almost all the early people were Cambridge trained. And the impact of their work was also somehow went in inverse proportion to their distance from Cambridge. So Bhabha's work was extremely influential because it was done right at Cambridge. Then people like Bose and things, so Bose was of course also a Cambridge product, but by then he had a big disconnect from Cambridge and his work, and the work of poor Taylor and Dabolkar was never known by anybody because they had sort of moved away from. So in a sense, a lot of the science being done in India was an adjunct to the science being done in Cambridge, and perhaps that was why it was very prominent at that time. So this is something to think about. So since independence, that umbilical cord with Cambridge has been cut, we have been on our own, and we have been doing whatever we have been doing. The second point is that all these people whom I mentioned, at some stage, at some very early age, they stopped doing science and or reduced their science, and they started became administrators, started founding institutions. Now, of course, the institutions exist, and we have jobs because the institutions exist. I'm not sure whether, but in a sense, the contributions they could have made to science were taken away by the effort they had to put into these institutions. So if there had been nice institutions anyway, these people would have continued to contribute more to science. So this is true for all these people. The third thing which you must have noticed is the very small number of women in this story, except for Bhabha Chowdhry, nobody. So this so half the population was not involved in this. So this is how it looked. And things have improved to some extent. There are a lot of discussion nowadays on this, but I think we are not very much better than this. To some extent, we have improved from that. But I will say this, these are the things which struck me, that these pioneers of science in India, they were like Davids facing Goliath, and they were fearless, energetic, and confident. They tackled cutting-edge problems without fear of failure or ridicule. Some of the ideas were crazy, some of the ideas were good, but that did not deter them. And they were willing to tackle the most difficult of problems with minimum equipment and sometimes money out of their own pockets, which was often true. And they had huge ambitions, they worked tirelessly, they had their own problems, they had egos, and they had their own fights, but they worked tirelessly, they were fulfilled. And I think this is the most important lesson to draw from their story. They were not deterred by the enormous obstacles they faced. And that's something which is, I think, a lesson to take home. Okay, thank you.